acquiring new trams and LRVs, light rail vehicles?
Light rail vehicles.
Light rail vehicles. When he joined VGF, he was originally in charge of infrastructure, depots, and vehicle acquisition. But as we're about to see, his role has expanded considerably. So a welcome, please, to Michael.
Yeah, thanks a lot. It's a great pleasure to be here and talk a few words about maybe the first steps of autonomous driving at the railway sector for trams. And the approach is a driver assistance system for collision avoidance for trams. That's the item which we had faced a few years ago together with a partner in Germany with Rüffer. I prepared a few sheets. One sheet about the situation in Frankfurt. Maybe it's interesting for the understanding. Then I will do speak some words about the ideas of the implementation of the system. And after that, we will have a close look on what's going on now and what we do in Frankfurt. So, Frankfurt, Germany, it's one of the biggest transport systems in Germany, but it's not so huge. But we have around about 118 million passengers per year, and we have two systems in Frankfurt. It's one so-called LRV system, it's more or less a metro, and a tramway system. And you see in this picture here, the tramway is in the normal traffic, and that's a problem, because there are a lot of accidents. You see here a data sheet of our safety management system, and it's in German, but you see here the accidents in normal traffic, and they were increasing year by year, and we thought about what we could do, and had discussions in the German group of transport authorities of the VDV. And then there was an idea, why don't we use automotive equipment, sensors which are available at the automotive sector, like radar sensors, video cameras or something else, and in order to improve driver assistance systems to avoid these accidents. So yeah, that was the aim. And I don't know if you ever thought about it, but do you know how to drive a tram? You drive it like a car. You drive it by sight. You are in the normal traffic, but you have only a few disadvantages. A weight of a tram is loaded about 52, 55 tons. And the braking deceleration is about a third of a normal car. So you have to drive carefully. And you have to have a close view on your track, and you have to recognize everything which is going on in front of you. And when you're driving, maybe for 3 or 4 hours, maybe especially in the morning, you will get a little bit tired, you will lose attention, and that's the critical point. So that's what the sheet said. You have, when you drive a car, always to be sure there's no obstacle on the track, and you have to pay always the right attention to the signals of your way, because you're in charge for maybe 200 or 400 persons in your car or in your double traction. So our idea was we would like to help the driver. We will give the drivers an additional sense for the recognition of track and obstacles in the track. And that's the main point of it. It was for us, for the legal rules, very, very important that we have not any violence of the regulations of drive on site. So it was necessary that the driver is supported, but is always the master on the train. So it means that he has always the right to overrule the braking system or the warning system or something else. So that's what this diagram shows us. It's a conventional tram, a conventional car maybe. You are the driver of the vehicle, you see a collision scenario, you see something in your way and you go on the brake with the feet and the tram with the left hand most of the times, and you do the braking alone. You decide what to do, you calculate the distance, yeah. You're the master of the tram. But our aim now was to give the driver an additional system, an assistance system, which is in parallel to the normal way. And that's shown here. It's the same thing. There's a collision scenario, but now there are two possibilities to go in a braking from the driver or from the assistance system. And yeah, to be honest, this idea was in the starting of our project not very common. Many people say, "Oh, that can't work, and that's a violation of the rules of the German legal rule. It's called BO-Strap, Bau- und Betriebsordnung für Straßenbahn." And we thought, no, we will try it, and we don't see that there's any violation of driving by line of sight if we have the possibility that the driver can overrule the system. Yeah. Very important was what operation modes we should implement for such a system. Should we only use a warning function, visual, acoustic, or combined, or should we do additional implement an automatic braking device? We decided from the first steps beginning that we would like to implement an automatic braking device, and yeah, we decided to put it. We'll show you later in a video by the master controller, and it was very clear in the first step that only a visual warning will be not enough for a stressing driver session on the tramway. So yeah. The system handling now at VGF, and it's yeah, I think it could be a blueprint for other systems in the moment in the LRV sector that we use. It's on the railway sector very common, a Deadman's device. Maybe you heard of it. Normally I do this presentation for guys from the railway sector, from LRV guys or something else. So it's a device that it's controlled that the driver is always on good health. So you have to push every 60 seconds or every station a button that the control unit and the vehicle is be aware that the driver is okay. So this is implemented in more or less every railway, and we use this as a triggering system for our driver assistance system. If the system detects an obstacle in the track, in the way, it will give you a beep, like the Deadman's device beep. And after that, you can decide for 2 seconds if you can see an obstacle which is not critical, so you can push down the master controller, everything is clear, you go on the handle as you like. And if you don't mention this obstacle in front of you, after 2 seconds and after the beep, you will get safety braking and the car is braking automatically. A big question was the choice of the right brake. So on such a railway, there are different types of brakes. There are a normal brake, which you use for a normal service brake for to go on a station, to stop at a station, and as well an emergency brake, especially for tramways, which is, yeah, I think by the power of 3, the deceleration of a normal station brake, of a normal service brake. So we did discussions with our authority, with our technical authority, and yeah, we integrated an external consultant to solve this question, and we came to the decision that we use a so-called safety brake, which is in the middle between a normal station brake, a normal service brake, and an emergency brake. And this was, I think, in our experience, the right decision. Yeah. And for sure, for our first steps, we hadn't the chance to implement the system in new vehicles. So it was not from the start of engineering in the system. So we had old vehicles, existing vehicles, and we had to build it in existing controllers. And so we decided that the Deadman's device could be a helpful decision. That shows what happens, what I explained, or I tried to explain. When you see here an obstacle, or the system sees an obstacle, it gives you a beep, a death triggering, and you have 2 seconds time to react on it, and if you don't do it, it will poke a safety brake. You see here, it's always possible that the driver puts on an emergency brake, that the driver overrules the system with an emergency brake. That's quite important because it's not really safe that the distance here between here and here is far enough to fulfill a completely brake with the service brake or with the safety brake. So that's one of the main facts of it. Maybe a little connection to the former presentation from Prickelbauer. It's a little bit a view to technology. There are 2 types of DAS, of driver assistance systems for collision avoidance, are now on the market. We call it a self-orientating or a comparative system. Self-orientating systems or comparative systems. And then self-orientating system uses sensors and a controller unit which calculates the whole environment, critical obstacles, right in time. So it was mentioned before, and this is critical. So it could be that there is high grass or a tree or an unknown person who's going straight in the way, but it's really far away, could be recognized as a critical obstacle. And so then maybe it results in a braking and in a stop of your service. The other possibility is to have a complete map of the whole system, to know everything about it, late in the vehicle, and the system will know, okay, when I go on line 1 and I will do a left turn, and there will be on the right side a pole maybe, and that's not critical because that's a pole and not a person or something else. Disadvantage of this, you have to know everything of your net, of your grid, and that's as well not so easy. In the next sheets or in our realizations, I will show you a few technical solutions for the self-orientating systems. And that's what we do. First, we have at Frankfurt 2 different systems in test service or in the first regular service, which are, the one is based on an automotive solution from Bosch, and it's a combined system from between a radar sensor and a video camera, which is often used for automotive suppliers. You see it here. It's as well at Östra in Hanover in Germany, and you see here the normal video camera, the radar sensor, and the controller box. When you see this equipment, it's automotive stuff. So I think they built over 1,000 in an hour or so of these modules, and it's very, very robust. It's very well engineered, and for us, it was an interesting thing to put this automotive equipment in a tramway car. So there are slightly differences in the electric wirings and something else, but it was possible to fix. So that's implementation you see here on the car. You see it's a so-called R-type car in Frankfurt. It's a hole for the radar sensor. Over there's the camera and the controller box is inside, and you see the same here. The radar sensor in front, camera between the screen, or behind the screen, sorry, and the controller box inside the car. So what does it mean? What's the result of these sensors? You see it here. It's a comparison between the radar dots and the calculation of the controller box. So the radar sees these blue points, obstacles. They don't know what it is. Here, this blue point here, this obstacle is a pole. So it's not critical, it's beside the trackway. The important thing is now that the mixture, the calculation from the video camera pictures and the radar echoes has to fulfill a completely safe side of the trackway in front of me. So I have to do, or the controller box has to do the decision if the pole is critical or not, or if this blue dot here is critical or not. This here could be critical. It's directly in the path from our train. So, and that's for sure exactly the problem. If you have a pathway in a curve, maybe in a left curve, so the video camera and the sensor will have a look straight away, and they will recognize objects, obstacles, maybe for critical, which are not in your right pathway because you go on the left side. Yeah, and that's now the point up to now. Yeah, and we have as well another system in service. It's from Bombardier and Austrian Institute of Technology, which is as well more or less common for automotive, but this is really tailor-shaped for railway applications. It's a so-called stereo camera. It's the same way in which we see. More or less, we don't have three eyes, so most of us. But in this solution, it's one camera is always fixed, and one is for the close view, and one is for the wide view. So because the three cameras, and these two different sides gives us a three-dimensional side of the track before us. So it's shown here in this picture. Maybe the principle and the controller box after that and the software is more or less the same. I have to recognize if there's something critical in my way, and I have to decide, okay, will it be critical for the further way of my tram or not? And you see here, it looks a little bit different. It's a monitoring of the system from the controller. It calculates here shapes of the tramway and makes a prediction of the way of the tram. And then it has a close look on it if there's any obstacle which is going in a critical way to the tram. So we'll show you, hopefully, a film. Looks good. So, you see it here? Yeah. See here the blue markings? So critical obstacle marked, and now the system will follow this obstacle, sorry, not target, obstacle, and will do it's more or less the same way, and will. You see here that yeah, and you see as well when it's the recognized critical obstacle leaves the pathway, then it's marked out. So no matter about it, doesn't make sense. Okay, that's the way how the system works, how the system sees it, but I think as well it's interesting to see how the handling of the system is. I mentioned it. It's a little bit too much lighted here, but you see here in the left hand of the driver, that's the master control of the tram. When I start the film, you will hear two beeps. The first one is from the radio, forget it. The second one is a recognition of the obstacle. Here's the obstacle, it's another tram which is standing still. And with our tram, we are driving in front, in collision to this other tram. We will have here the second beep, and we will recognize the automatic braking. That's on. This here. Here the beep was the 2-second beep, and it would be possible for it would have been possible for the driver to overrule the automatic braking by an emergency brake. Jetzt, ne? Yeah. So that's the point on for us now. In Frankfurt, there are some other developments now. In the sector, there are lots of tests of systems from IET Bombardier, from Bosch, and especially Siemens is doing especially tests for the right sensor. It's now a little bit a battle for the right sensor. Should we use radio camera or stereo camera or a laser scanner or a map, which was as well in use here at Vienna a few years ago. Up to now, it's not clear what sensor will be the best one. I think it depends really on the environment in which you are driving your tramway. But it's recognizable that these DAS systems for collision avoidance are now going to be the state of the art for the new tramways of the next years. So in maybe more or less every LRB specification, you will find a notice about DAS. So when you see here, it's from a Siemens prototype at Ulm. They are testing here different radar sensors and laser scanners and so on. At Frankfurt, we have now, since last year, the approval from our authority for the service of for the regular service of both systems, and it was a picture from our homologation test. And up to next year, we will have all our 74 S-type cars, which is here the yellow one, fully equipped with this DAS system, and It's a very exciting moment for us now. Yeah, what was our experiences in the engineering? It was for us very good, and this is not very common in the railway sector, that we did the engineering and the development together with a partner from another transport company, which is Östra at Hannover, and as well with Bosch, Bombardier, and IET. It provided very quick solutions, and especially the handlings for the driver is very easy and got quite a huge acceptance in driver's department, which is the most important thing. You have to be ensured, because when the drivers don't like the system, you can forget it. So yeah. It was as well interesting to see the comparison between automotive hardware, software, from standard, from normal automotive fabrication, and in comparison, the tailor-shaped railway application. It has advantages and disadvantages, and it's not easy to say which system is better or less better. They have all a plus or the minus of all system, but it was very interesting to have a close look on the possibilities in the automotive sector, and I think that this will be only a start for the future of railway engineering. There will be lots more of items to get from the other sector. Yeah, and a special very exciting thing was the homologation of these systems, because there wasn't ever any homologation of a driver assistance system. So there was no tests, no rules. So you have nothing, and you have to decide, we have to get an homologation for it, but how? Don't know. And we talked with our authority, we talked with Bosch and Bombardier, and we made a solution, a tailor-shaped solution for the homologation with a close look to automotive sector with ANCAP regulation and something else. And everything said, well, many people said in the starting of the project, you won't ever get a homologation of this stuff because no authority will give you an approval for it. And the experience shows that with a close link to the authority, it was not a real problem. Yeah. Our operations experience is, very interesting. As I said, there are differences between the two systems, but you can't say which is better or less better. It's very important that you have for the test of several hardware or software releases a fixed testing procedure, because testing of such a system goes a little bit from the stomach. So it looks good, it feels good, it's not so good. I think this pole was not recognized before something else. So we decided our internal testing approval comes from the same driver on the same track. So we have a route through Frankfurt, which is our testing route for fast, and you could see very easily then when you get a new software release, if you have a real improvement or not. So that was for us very important. And it looks like that these self-orientating systems could be, as in the speech from Briggelbauer, could have been limits. So if the system must recognize, calculate, decide everything around in real time, it looks a little bit that it could be different, especially when it goes in a curve, or when you have switches before you or something else. The track prediction is not so easy. So it seems to be that additional in future there could be an automatic device very helpful. Yeah. The next step, I think the last step should be as well autonomous driving. You can't explain anybody that a car could drive autonomous, but a tramway can't, because it's not safe. Okay, we're driving on a fixed track and we have a fixed route. Okay, but we can't do it safe. I think that won't work. I think in the template it was shown before in the first presentation today, I think in 5 years we will always see in our cities autonomous driving vehicles. It would be normal. And I think it will be as well necessary to think in this way for railways, or especially for tramways. But if we want to do this, we have to think over our existing legal rules. We have to adopt them. We have to review them. That's quite important. And I think from the German point of view, especially for the traffic, for the car traffic, it's up to now as well the critical point. The technology, I think, is there. You can use it, you can try it, you can implement it. That's not the problem. Before this maybe last step, there are lots of things you can do in the way to it, and I think that's that as well the point which we learned from that in this project. Normally in the railway sector, you want from high floor to low floor, from from no customer service to full customer service. You want always have a solution from 0 to 100%, big steps. And between that, when you get your new train or your new infrastructure, you see, oh, it doesn't work, we have to re-engineer it, we have to re-implement it, and something else. And we did it here in a completely different way. We use small steps. We said first, when we started, okay, we want only to recognize a tramway in the track before us. a huge obstacle. And when we learned, okay, it works, and yeah, we could recognize smaller items, smaller obstacles. We said, okay, let's try it. Let's try to improve the software and the controller, and it works in the same way. And when we continue in these small steps, especially for new vehicles, there are lots of interesting features which could be implemented without big problems. Maybe traction or power interrupt, optical or acoustic warning for crossing pedestrians, maybe, or something else. Speed limitation, switch or signal monitoring, which is a main course for accidents in the railway sector, or here as well, communication with other trams or cars. The video we saw in the morning. It's essential to have communicating trams in daily traffic in our cities. So, yeah, that's what I have to say about what we do in Frankfurt. Hopefully it was a little bit interesting. It's a completely different sector here for the audience, but yeah, thanks a lot for your hearing.
Michael, thank you.